Welcome to the fourth and final part of EEE 157 Lecture 9, Week 9, Digital Modulation Techniques. In this part of the lecture, we will be analyzing the different properties of your different constellation maps, of your different bandpass digital modulation techniques. Okay, so first things first, how do we determine the energy given a constellation? So each transmitted symbol S sub m consumes energy E sub Sm, which can be calculated by this equation here. Quite simply, the energy of a symbol is equal to the magnitude of that symbol squared. So if we have a constellation, given a constellation, you get the coordinates of the symbol. Okay? Take the magnitude of the coordinate, square it, you get the energy of that symbol. Okay? Let's say the probability of this symbol S sub m is given by P of Sm. For m symbols in a constellation, we can compute the average energy per symbol, or the expected energy, using this formula right here. You basically just multiply the probability that symbol S sub m is transmitted to its energy. That's here. And you add that all up, you get your average energy. Okay? So substitute the energy of a symbol, you get this equation right here for your average energy per symbol. If we assume that the symbols are equiprobable, then this P of Sm here will just be equal to 1 over m, m being the number of symbols in your constellation. So quite simply, you just compute for the average energy energy per symbol. You get this nice formula here, which is simple enough. Just add the magnitude square of the symbols inside the constellation. Okay. So another parameter we want to look at is power. How much power do we need to transmit given the bit rate and given the number of symbols, okay, and the probability of each symbol. So normally we just assume that the symbols are equiprobable. So now another parameter of interest, so that we can easily compare between two different modulation techniques, is the energy per bit. Okay. So some techniques use more symbols. It's not fair to use the energy per symbols to compare it to another technique. So the bottom line is we use the energy per bit to compare between them. And the energy per bit is quite simply the energy per symbol divided by the number of bits used per symbol. Okay? So if you perform dimensional analysis, the units should be consistent. This is the energy per bit, so this is in joules per bit. The energy per symbol will be in joules per symbol. And the number of bits B here is the number of bits per symbol. So if you perform dimensional analysis, the symbols will cancel out, leaving you with the units joules per bit. And if you substitute that, okay, we know that B here is the logarithm of m base 2. So substitute that here. And E sub S, the average symbol energy, can be taken from here. And we have this equation right here. If the symbols are equiprobable, then P of Sm will just be a constant 1 over m, and you got this formula for the energy per bit. Now to compute the power, assuming we have some symbol rate R sub s, that's the number of symbols we transmit per second. Okay? The power consumed by a constellation is quite simply the symbol rate multiplied by the energy per symbol or if you're given the bit rate and the energy per bit, you just multiply the energy per bit with the bit rate. And if you get the dimensions of this, if you perform dimensional analysis, R sub s is in symbols per second, okay? And energy per symbol is joules per symbol. So the symbols cancel and you'll be left with joules per second, which is a unit of power. Similarly, that's what you get when you perform dimensional analysis for the bit rate and the energy per bit. Okay? And that's how you compute the constellation power. Okay? Next thing we need to evaluate or we need to know is the relation between the minimum distance and the reliability of your signal. So as you know, the signals that you receive can be corrupted by noise. So it could be corrupted by noise. The range of signals that you'll get could be here. Okay? If the noise is large enough, then the range of signals would be here. there's a probability that the received signal will cross over this line here. This line here, the green line, represents what we call the decision boundary. Okay? And it forms the decision regions. If your signal falls within a boundary, the receiver will decide that the received symbol is the one closest to it. So if you receive this symbol here, it's close to S2. Therefore, the receiver will say, this is S2. Okay? But if you transmitted S1, you receive this, that means the noise is very large. And you have a bit error. Okay? So if you space the signals far apart with the same amount of noise, there's a less chance for the received signal to go over the boundary. Therefore, we can use the minimum distance as a measure of the reliability of your constellation map. So if you have a larger minimum distance, your constellation map is more reliable. Okay? Because the probability that your receiver will make a bad decision will be less. Okay? So that means that the minimum distance, let's call it dmin, has an indirect correlation to the probability of error. Okay? So let's compute for the minimum distance of your example modulation techniques, the MPAM, MASK, PSK, and QAM. Okay? So given the constellation of MPAM, let's say you have M symbols. Okay? Let's say the distance between them is D, minimum distance. Then your constellation will be defined by these integers here, or sorry, in these with these parameters here. Okay? So let's assume this is S1 and this is S sub M, big M, right? So the energy of one symbol can be defined by this equation right here, where M is an integer. So I did not put it here, but the M is an integer from 0 to M minus 1. Okay? So the energy of the mth symbol is equal to the magnitude of the symbol squared. So you get this formula right here. If we want to get the average energy per symbol, then if we assume equiprobable symbols, then we can simplify this. Okay? Divide it by m, and you get this equation here. You sum this all over all symbols m. Okay? You perform a bit of integer algebra here. So this equation here will actually simplify into this. And if we get the energy per bit, you just divide this by the logarithm of m base 2. You get this equation right here. Okay, so the energy per bit is dependent on the minimum distance of the bits and the number of bits per symbol right here, or the number of symbols. So the energy per bit is dependent on the number of symbols and the minimum distance between symbols. Okay? And this is how we quantify the dependence between the energy per bit and the minimum distance. As you can see, if you want to have a greater minimum distance, you need to use more energy. Okay? So this is the proof of that. For PSK, quite simply, since the PSK has a constant amplitude, so all of the symbols have the same magnitude A, the average energy per symbol is simply A squared. But if we look at the average energy per bit, we have this value right here, A squared over log M base 2. So how do we relate it to the minimum distance between symbols? First, we need to express A as a function of the minimum distance between symbols. Okay? So to do that, we'll just need to use a little bit of geometry here. Okay? So I'll leave it to you actually. So this is a geometrical problem. You have a hint here is you have a vector from here to here, and you have a vector from here to here. You take the difference of the vectors and get the magnitude, and you will get the minimum distance. Okay? And that's my hint to you. Okay? So, and this distance is the same for every symbol that you get. The same distance. So the amplitude, which is the radius of this circle A, is related to this D by this equation. M here is the number of symbols in your constellation. So knowing that this is A, substitute that back to your average energy per bit, and you will see that similar to ASK, if you want to increase the minimum distance per symbol, you need to increase the energy of your transmission. Okay, so basically there's a trade-off, right? If you want to increase your energy, your minimum distance, your reliability, you need to increase the energy. Okay? Similar to MASK. How about for MQAM? Okay? So for MQAM, I won't show the derivation anymore. Okay? The average symbol energy is defined by this formula. Okay? And the average energy per bit is equal to this. So similar to both PSK and ASK, QAM, if you want to increase the distance between symbols, you need to increase the average energy per bit. Okay? You need to increase the power of your transmission, basically. Okay? And for MQAM, the boundaries, well, you just need to set the boundaries in between your symbols right here. I forgot to mention earlier that the green lines here are the decision regions for your PSK. Okay? If you want to increase if you want to increase the area of the decision region, you need to increase the power. Okay? Okay. So we can now express the minimum distance as a function of the number of symbols in your constellation. Okay? And it's also a function of the energy per bit of your constellation. Okay? Generally, as we increase the number of symbols in the constellation for a constant energy per bit for all the different techniques, see if this is constant, 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 you can see that the reliability, which is the minimum distance, decreases. Okay? So, if M increases, well, what's the trade-off? So if that happens, why don't we just reduce M? But if we increase M, we're having a larger bandwidth efficiency in the communication. Why? Because if you transmit more bits per symbol, maintaining the same symbol rate, if you maintain the same symbol rate, you maintain the bandwidth of your transmission. Okay? But if you increase the number of bits per symbol, you're increasing the bit rate even if you're maintaining the bandwidth. Okay? So if you're maintaining the bandwidth but you transmit more bits per symbol, you have a larger bit rate. Then you're using your bandwidth more efficiently. Okay? And that's the trade-off. If you want to be more bandwidth efficient, you need to use more power so that you have to maintain the same reliability. Okay? So D here, if you want to maintain D, if D is constant, if you increase M, you need to increase E sub B. Okay? And this is shown here. For a constant energy per bit, this is your plot here. The minimum distance is larger for QAM, as you can see here. For all cases, QAM performs better for a constant E sub B. Okay? What's the trade-off? It uses more computational complexity compared to PSK and ASK. Okay? It uses more computational complexity compared to PSK and ASK. Okay? So this graph can show you a lot of information. If you have a larger number of bits per symbol, then your minimum distance decreases as our this is our prediction. Okay? So what about MFSK? Similar to PSK, the energy per symbol of FSK is only dependent on the carrier amplitude here. If you have the definition of MFSK here, the power of your MFSK is quite simply a squared over 2. Okay? This is a sinusoidal carrier. So the power is equal to the amplitude squared divided by 2. Sorry, the energy per symbol rather is equal to a squared over 2. Okay? Therefore, the energy per bit is a squared over 2 log of m base 2. How can we relate the minimum distance per symbol to the amplitude so that we can get the relationship between the energy per bit and the amplitude? As was our exercise in the previous examples, we want to know the relationship between the energy per bit and the distance between symbols. So you need to recall the fact that for FSK, the symbols are orthogonal to each other. Okay? The symbols are orthogonal to each other, then if we put them in the constellation, the magnitude of each symbol is equal to a over square root of 2. Where did that come from? If we have the energy per symbol given to be a squared over 2, which is equal to the magnitude of the symbol squared, then the magnitude of one symbol is equal to a over square root of 2. And that's how we got this magnitude here. Okay? So it's orthogonal. That means the different symbols exist on different axes. Okay? So if they're orthogonal, how do we compute the distance between them? We just need to use Pythagorean theorem. The two symbols form a right triangle since their axes are orthogonal. The sides of that right triangle are both a squared over square root of 2. We can compute for the distance between them using Pythagorean theorem, and you get this value here. Quite simply, the carrier amplitude is equal to the minimum distance between symbols. Okay? Therefore, E sub b is equal to d squared over 2 log of m base 2. Okay? So if we get the minimum distance of a function of m and E sub b, actually, if you increase m for FSK, you're actually increasing the minimum distance between your symbols. Okay? So this is in contrast to the behavior of ASK, QAM, and PSK. So that means for FSK, we should just use a lot of symbols, right? Well, the limiting factor here is that it uses more bandwidth. So since FSK uses more bandwidth if M increases, okay, and if we're bandwidth limited, we can't really use FSK practically for our communication system. Okay? So in terms of power efficiency, however, FSK is better than ASK, QAM, and PSK. Even if we have a very low E sub b, we can maintain a large reliability if M is greater. So if this is lower, E sub b is lower, then M should increase so we can maintain the same reliability. Okay? So this is in cost of larger bandwidth use in the system. But we can call FSK as a power efficient technique. Okay? If ASK, PSK, and QAM are bandwidth efficient techniques, FSK, on the other hand, is a power efficient technique. In that, even if it uses less power, we can maintain its reliability by increasing the number of symbols. However, it uses a larger bandwidth. So, if it's using a larger bandwidth, it's not that bandwidth efficient compared to ASK, PSK, and QAM. In conclusion, therefore, your power efficient technique cannot be a bandwidth efficient technique for a digital communication system. And this is an inherent trade-off found in a digital modulation or digital communication system rather. You can find this in an analog communication system where your power efficiency has a trade-off with your bandwidth efficiency. Okay? And just to compare between ASK, PSK, QAM, and your FSK, as you can see, your FSK increases in reliability as you increase the number of bits per symbol for a constant energy per bit. Okay, so FSK is preferred to be used when you want to be efficient in power. And an example of that actually is the LoRa protocol, or the LoRa technology. So we can search that. LoRa uses a large bandwidth, okay, to transmit long distances, and it uses a very small amount of power only. So this is a prime example of that. It's a technology that uses FSK to transmit its data, and LoRa is very useful for wireless sensor networks. So you can read more about that, okay, if you want to dig deeper into this concept. Okay? So just to summarize, then, your constellation maps are very useful tools to visualize your set of symbols that can be used that are used by a digital modulation technique. So with the constellation maps, you can form decision boundaries. So it can be visualized using a constellation, using your constellation map. Okay? You can also solve for the minimum distance between symbols Since the minimum distance is just a geometric problem using constellation maps, you can now easily solve for the minimum distance given a constellation. Okay? And there's a behavior in ASK, PSK, and QAM that if you have a constant energy per bit, the distance between symbols decrease if you increase your number of bits per symbol. But the opposite trend is observed in FSK. And finally, there's a trade-off observed between your power efficiency and the bandwidth efficiency in your bandpass digital modulation. If you want to be more power efficient, you use more bandwidth. If you want to be more bandwidth efficient, you use more power. Right? And this is true for any digital modulation techniques out there. Okay? So that's the end of this lecture for this week. If you have any questions, do not hesitate to leave a comment in the comment section below. Okay? Just for your reference, you can find more information about digital modulation techniques in these books. Okay? So for these two, you can find your baseband and bandpass. Okay? For this one, you can find your line codes. And for this one, your bandpass modulation techniques. Okay? Just a note for this book, it's very heavy in math, so we didn't dive deep into the math here, so you may be you might be uh, surprised by the amount of math here in this reference. So thank you for listening, and I'll see you next meeting.